Now, in terms of our first interpretation, our interpretation of the first integral, where v of t is velocity, and your antiderivative function, the change in your antiderivative function, therefore represents change in position because of what the average velocity and time interval tell you. Okay, I'm going to say that any antiderivative of this function would be a change in position function. I could add any constant here, and we would still have a change in position function. If I added 10 to this, well, that would increase this to 130, increase this to 2402.25. It would increase both of these numbers by 10, so the change that you get when you subtract the first from the second is still going to be the same. So any antiderivative function I choose, any antiderivative function I want to construct by letting the constant be anything I want it to be, we're still going to have a change in position function. The position function is the appropriate antiderivative function in a way that I'll amplify on here very shortly. Okay, this means that if I'm measuring the position relative to some point, so if this point is the 0 position, then I have to choose my constant so that this antiderivative function is 0 at that position. So, and depending on the units I use and the position I choose as my reference position, I'm going to get different antiderivative functions for different choices. So what we have for our first example, v of t was 2t cubed minus 3t plus 4. Antiderivative was t to the 4th over 2 minus 3t squared over 2 plus 4t plus c. This is our general antiderivative. Okay, general antiderivative, where we understand that c is a constant and c could be anything, so there are infinitely many possible specific antiderivatives. Now, any of our antiderivative functions for any value of c is a change in position function, so that we can evaluate any specific antiderivative at t equals 4 and t equals 7 and get the change in position between t equals 4 and t equals 7. This works fine for any change in position. The antiderivative function for c equals 0. We don't need to carry that c around. The change in this function will be our change in position. Now, what if we want a specific position function so that we can plug any clock time in, any value of t, and get a position relative to some known position? Okay? Well, let's find the specific function if we know that the position is 10 when clock time is 2. Now, we're not using units here. We generally will use units, but let's just get the idea and not worry about the units right now. So maybe position is 10 meters when t is 2 seconds. Maybe position is 10 kilometers when t equals 2 hours. Could be any set of units. This could apply to any set of units appropriate to whatever the situation might be. Okay, well, let's let the position function be s of t. And we know that the position function is one of our antiderivative functions. That's t to the 4th over 2 minus 3t squared over 2 plus 4t plus c. We don't know what value of c is going to give us the correct position function for this situation, but we can easily find it. Okay, so what do we know? We know position's 10 when t equals 2. That means the given condition is that s of 2 equals 10. Okay, s of when t equals 2 has to come out to be 10. So let's see. S of 2 is what? It's 2 to the 4th over 2 minus 3t squared over 2 plus 4t plus c. Well, that equals what? That equals 2 to the 4th is 16 divided by 2, that's 8. T squared is 4, divided by 2 is 2, times 3 is 6, it's minus 3. And then this is plus 8 plus c. And that equals 10 plus c. But of course, S of 2 has to equal 10. So 10 plus c has to equal 10, which implies that c equals 0. So in this case, it looks like we probably started our timing, it looks as though we started our timing at t equals 0, which point the position function was 0. Now we're not going to get into that right now. Okay, but in any case, this is a procedure. We assume our general function and we evaluate our constant, and we then throw our constant in. So S of t is just t to the 4th over 2 minus 3t squared over 2 plus 4t. Now, this position could have been measured differently, okay? This position might have been 50. If this position was 50, then we would have gotten 10 plus c equals 50, so that c would be 40. Well, this is something that I'm sure you've done in your introductory calculus class. If you haven't, please let me know. I'll give you a little bit more information on it, but it's something you want to review. Quickly note that I wrote t squared here and t here, and I should have substituted 2 throughout, so I've corrected that, but there should be no confusion over how we evaluate this at 2. Now, what if we had a different given condition? Let's just say that somebody said, oh, darn, I read the clock wrong. When it was at the position 10, the time was 1. Okay, well, then we'd have S of 1 equals 1 to the 4th over 2 minus 3 times 1 squared and so forth, and we get 3 plus c. So S of 1 would be 3 plus c. But now S of 1 equals 10 from our new information, and it follows that 3 plus c would have to equal 10, so that c would equal 7. And it follows then that our S of t function is going to have c equal 7, and it's going to be t to the 4th over 4 minus 3t squared over 2 plus 4t plus 7.